All right, well, so one of the things we saw with James's in situ matchups with the satellite data was the scatter plots and Bland-Altman plots, but we might have noticed there wasn't an explicit mention of the time dependence. And of course, as we're making these time series and gathering this data, it's done at certain times, so that might be something that's relevant to our analysis and something we might want to know. So earlier this morning, we heard Kelsey Bisson talk about looking at these matchups and noticing at certain parts of the year the disagreement might be worse, and whereas other parts of the year might be better. So that hints at some sort of oscillation. So if there's an oscillation in our time series, how can we detect it? And more specifically, how can we, if there is this oscillation, how do we know what frequency it's oscillating at? So this example is going to be using validation matchups, hence why I'm talking after James. And so we're going to try to see if we have any oscillations in our remote sensing reflectance data. So given a question like that, I think it's always easier to, let's see. Whoop. So given a question of like, okay, is there an oscillation in our data? I think a good thing to do, and a practice that's always good to do, is start with a related question, but one we already know the answer to. So here's a time series scatter plot of the solar zenith angle, something that we know oscillates with time. So if we look throughout this matchup data collection period, we see this clear oscillation, whereas when it agrees with our intuition that the solar zenith angle is lower, closer to the horizon in the winter and higher in the summer. And if someone was asking, hey, does the solar zenith angle oscillate with the time of year? You would, one, hopefully already know it, but if you looked at a scatter plot like this, the answer would be quickly and readily available. But what if it's not so clear? So here are now time series of the difference between the remote sensing reflectance between the satellite retrieval and an in situ site. Here it's MOBI. And then also the remote sensing reflectance from both the satellite and MOBI with time. And so now if we were going to ask the question, is this data oscillating with the time of year, or really any sort of oscillation, it might be there, but it's much harder to tell and discern. So is there a tool that we can use that makes this more quantifiable? And there is, and that's a periodogram. So typically a periodogram requires really regular data sampling because it uses a Fourier transform. Given satellite data, if that revisit time was once per day, you would have to have every single sample happen 24 hours later for your entire range of data series if you were to use a direct application of a periodogram analysis. Obviously, for many reasons, that's not really possible. One that James highlighted was the stringent validation criteria, so we're actively throwing out data that doesn't work. And so if you do that, you would have this irregularly sampled time series, and you couldn't necessarily just quickly generate a periodogram. But fortunately, there is a way around that, and that's this modified periodogram called the Lomskargel periodogram. So what does that look like? And again, starting with the solar zenith angle, where we already know there's this oscillation. We see on the y-axis is this metric of power, and importantly on the x-axis, this is a period here, and we're looking for where peaks might occur. And so there's this dominant peak at a period of 1 year. So for every year, there's a single oscillation in our data, in our time series, which is exactly what we expect for the solar zenith angle. But now, if we go to the remote sensing reflectance data and generate the same periodograms, we can also see that this oscillation occurs where every year there's one oscillation. And so why is that helpful? Well, we can go and fold our data to a new scatter plot. So instead of the range extending across the entire temporal range of our data collection from day 0 to our last day, we're bending it all into 1 year, because that's where we know this oscillation occurs, as we saw in the periodogram. So in this representation, where everything's within this range, we see this dependence with the time of year much clearer. So on the left is the difference, and so we can see that these validation matchups have some sort of dependence on the time of the year the data was collected. So in the winter months, which is at the edges of the x-axis, we see that the bias is such that the MOBI data is measuring something a little bit higher than the satellite, whereas conversely in the summer, satellite's measuring a higher remote sensing reflectance than MOBI. And similarly, just looking at the time series of remote sensing reflectancies, we see this pattern also exists just in the raw data. And that's really all I have for this notebook, but really the main point here is that this is not only relevant to remote sensing, directly related to the remote sensing reflectance data. This is really applicable to any time you have a time series. So anytime you have a variable and an associated timestamp and you're wondering if there's an oscillation, this tool will be really useful to, one, detect that an oscillation exists, and then characterize that oscillation. So is it happening once per year? Is it happening every 3 months? Is it happening every day? Depending on how much you sample your data, you can answer these questions. So if that's something that you think would be helpful, I think the most obvious use cases would be out like chlorophyll concentration with time, or even outputs from Moana, and looking at those different groups of phytoplankton. It would be cool to see how that oscillates and what frequency it does so. So if that interests you, please just pull up this notebook. There's a lot more there. There's references to the papers talking about this in much more depth. And of course, I'm here to answer any questions. So that's all. Thank you.
Yeah, really. It's probably in the paper, but what is responsible for the bias between MODIS and MOBI in like the summer, let's say?
Perfect. Great question. So one, we're identifying it, but two, there's a lot that goes into it, right? So remote sensing reflectance isn't directly measured. It goes through this entire processing pipeline. It turns out that everything really depends on the sun, especially in radiometry. So we're measuring this intensity. How bright the sun is directly related to that. But in our atmospheric correction process, right, there's parameters like wind speed. There's parameters like air pressure and chlorophyll concentration. All these go into play. And because they're all related to the Earth, and the sun is really relevant to everything that goes on the Earth, they all oscillate with this frequency. So anytime we have sort of this anytime something's not perfect, the way when you subtract two sine waves, you're going to get another sine wave, and so you'll see this bias. So one answer to your question is everything, and just by the fact that there's always going to be uncertainty in our data. There's probably specific places improvement could be done. I don't know what those are yet, but the idea is that given that this exists, just account for it with your uncertainties. Yep.
Yeah, that was really cool.
Appreciate it.
I just wanted to mention that the Loam-Scargill periodogram is also really helpful in the spatial domain as well,
Probably
which,
cool.
especially for satellite data when you're screening for clouds, and you have gaps in your data sets always. And I've actually used it to, there's for any sort of turbulent fluid, there's an expected distribution of the turbulent cascade, how much energy is at each scale. So for clouds, you can actually take a periodogram of the spatial variability of, say, cloud optical thickness or liquid water path or something, some conserved variable. You could even do this for any sort of biological variable if you wanted to as well, because it should be a tracer for the fluid generally. And you should be able to track things related to the actual fluid dynamics as well.
No, that's really awesome. Yeah, I hope we talk more. That sounds really cool.
What would be the kind of acceptable minimum sample size for that to work?
So, loaded question, right? So there's actually very strict criteria for your standard periodogram, where you have the regular sampling and there's the Nyquist frequency, and you can never get better than that. So you have a very finite limit on how high of a frequency you can measure. It turns out the randomness injected into your measurements when you are removing data and have this random data selection, it actually can perform better than what's expected, which is counterintuitive, right? Because it seems like you have less data, but because that data could be a little bit later, a little bit earlier, it helps fine-tune the model. But the exact answer to what those limits are, there's a lot of work done, and they're kind of ambiguous because it's hard to know if it's just pure mathematical theory or if it's really actually relevant to data that has this biases and uncertainties. So the answer is, that's a great question, but and it might actually be better than what's typical, but it's people are studying it. Yeah, thank you. But I should add, one great thing about the Lom-Scargill periodogram in this package we're using in Python is that there is a sort of a very easy metric to get at. It's called a false alarm probability. So given a peak, you can ask it, okay, what's the likelihood that this is an actual oscillation in our data? And it accounts for things like your sampling and also the uncertainty in your data. And it can say, hey, this is more than likely than not just a random occurrence due to the fact you don't have enough points and there's uncertainties. Or it can say, hey, you have so many points and this uncertainty is this much, therefore this peak is likely really significant. And so you can have a metric for that, and that's in the notebook. It's called the false alarm probability.
Other than the false alarm probability, are there other things that tell us if a queue had nice clear peaks?
Yeah.
And basically, if you get multiple peaks and you still detect whether they're significant or not, or just false alarm probability found only for the main peak clear?
Yep, no, so another great question. So the analogy here is, or I'll start with this. There was reason for us to believe that the annual periodicity existed in our time series because of the sun. So we started there, looked for that, saw a peak there, and then so those metrics are very accurate. Alternatively, if we really had no idea what peak we were looking for, and we looked across this entire range of the periodogram, and a peak occurred, there's a strong likelihood one's just going to occur randomly. So if you have a 1 out of 6 chance to roll a 6 on your dice, you can roll that dice once and look for your 6, and that's 1 out of 6. But if you just roll a lot of dice and look on the ground, one of them is going to be a 6, so you can't really use the same statistics. The false alarm probability does account for that, and that's kind of the point. So yes. Mm-hmm.
All right, thank you, Riley. That was awesome.
Perfect, thank you. Appreciate it, guys.